Has been around and in the CS department since I joined, but is a very recent addition to the field of applied mathematics. It does a variety of interesting physical simulation stuff and optical light transport calculations in particular for computer graphics. And today is talking about simulations of optical scattering and some wave phenomena that appear in graphics. And with that, I'll hand it off to you.
All right, thank you. In my usual life, I spend most of my time thinking about light transport and geometric optics, and this is sort of the bread and butter of rendering for computer graphics. And so what I'm talking about today is kind of atypical in this field, which is looking at some of the predictions of the wave model of light. I want to spend a little bit of time setting up. I try not to spend too much time setting up, but tell you a little bit about the phenomena of light reflection from surfaces and fibers that we're interested in modeling. What are the kinds of things you see? What are some of the classical scattering models that get used all the time for these kinds of objects? And then look at some of the questions that these previous things left unsettled about what actually are some of the approximation errors that we're losing or that we're incurring by assuming wave optics, by assuming ray optics or by assuming simplified models of wave scattering. And I'll tell you about a couple of simulators that we have built that have the goal of trying to come up with a pretty accurate solution to a wave scattering model that actually solves Maxwell's equations for reflection from these structures so that we can get either some information we can use to do renderings or some information we can use to kind of evaluate other models and understand how well they're doing. I have 3 projects to talk about, although experience suggests I may only get through 2. Okay, so let me get started. Starting at the very beginning, when you have light interacting with some material, usually the light is interacting with a 2-dimensional surface of the material. It's a boundary between two types of material. Very hundreds of years old physics can give us very accurate predictions for what happens to light reflecting in the smooth boundary of a conductor or dielectric. Conductor, of course, only reflects and it isn't able to transmit light through it. And a dielectric material can have a reflected and a refracted ray. If only this was the whole story, we would have been done a long time ago with modeling materials for graphics. But unfortunately, materials persist in not being nice, smooth, polished materials. And so even if they are pretty much pure conductors or pure dielectrics, the surface structure has a lot to say about how it reflects light. So for instance, something that occurs all the time is you have a conductive surface that's just rough, so you have a metal that's not polished. And what you see is a sort of diffusive scattering where light coming from one direction will spread out to a range of directions, but still mostly going near the mirror reflection direction. Or if you have dielectric materials, you very often see structures like this chalk here where you have lots and lots of little bits of stuff in the subsurface. Light will go in there and bounce around like crazy and forget where it came from so that it comes out in a very uniform way. So these phenomena are kind of the basic things that we expect to see, that our standard models expect to see. We have pretty good models for these kinds of reflection. So the function that we use to describe the material classically is called the BRDF, which is for bidirectional reflectance distribution function. So if I have a surface that is homogeneous across the surface and it's going to reflect in the same way everywhere, then I just need one such function to describe the whole thing. And so what the BRDF is a function of 2 directions. That's why it's called bidirectional. So one is the direction the light is coming from, and the other is the direction the light is going to. And its job is to tell you what will happen if you take this piece of material, you illuminate it from omega I, you look at how much light went toward omega O, and it roughly gives you sort of like what fraction goes toward omega O. So it's a function of 4 variables if you list them out as scalars, and often we use theta and phi angles like these in a spherical coordinate system. I'm going to try to stick with I and O for incident and outgoing. Hopefully I've expunged various reflected and exiting and other things. So if you look at the models that are used for this in rendering or in computer graphics generally, most of them are from what's called the microfacet family. And the idea here is to use a ray optics model and assume that what you have is a surface that would be a mirror if only it was flat, but it's got little bumps on it. And so the little bumps are important because when you take a bunch of light rays, like these parallel ones coming in from the right, they hit the surface and they see different surface normals locally, and so they reflect into different directions going out. And so the question that's posed here is when light rays all come in from the direction omega I, how many of them will go in the direction omega O? And you can think of this as a probability question, sort of what is the probability density with which these rays come out going in the direction omega O? So it turns out it's pretty easy to answer this question because a ray coming from direction omega I will go toward direction omega O exactly when the normal is halfway between those two directions. And so all I really need to know is what's the probability of the normal being right. So if I have a model for the probability density of normals over my surface that says maybe one's pointing straight up or most likely and one's pointing very much to the side or less likely, then I can make a simple model. So this is the sort of dominant mindset for modeling these things. I'm not working all the way down to a model here because I'm not actually going to use it. On the other hand, there are many similarly old models for surface reflection, rough surface reflection, that are not based on rays but are instead based on a wave model. And almost universally, these are based on scalar diffraction theory. And so the idea here is that the question is posed a little bit differently. And I guess I realize I've swapped left and right too. But so now the incident light is coming from over here. Instead of saying I have a whole bunch of parallel rays coming in, I say I have a plane wave that is incident from that direction. And the question is, if this plane wave is incident on the surface, how much light am I going to see in some outgoing direction omega O? And so here, we'll talk about a little bit later how to do this really accurately, but the standard assumption that is made to keep things simple is to assume that I can actually, just by looking at the value of the incident field at a point on the surface, so I have this plane wave that is giving me a sinusoidal variation in the field. If I evaluate that on the surface, I can point-wise calculate what the reflected field is going to be. So this is assuming that two different points on the surface don't interact with each other. It's assuming a lot. But if the surface is very gently sloping and has very low curvatures, this is a pretty reasonable assumption. So I basically assume at each point that I have a plane wave reflecting to another plane wave. Use that with the classic Cornell model that I would use for a perfectly flat surface to come up with a reflected field on the surface. And then I can use a diffraction integral that will let me integrate over this surface to predict what the field is at some point out there in space. And in particular for a BRDF, I'm interested in sort of in the limit far away in some direction. What is the field intensity? And so these models generally are set up to average over some random process so that the answer they give you is not for some very specific little chunk of material, what is its scattering behavior, but averaged over some random process that will generate as many examples as you want. What's the mean light that you see? So this is another kind of model that is used, and it produces predictions that are similar to the microfacet theory in a lot of ways, but have some differences and are generally more accurate, although they're a little more expensive to evaluate, so usually we use the microfacet models most of the time.
Sorry, just to get an idea of the scales, how does the wavelength compare to the scale of the imperfections you're talking about in the surface?
So for the ray model, it had better be smaller than the scale of the imperfections on the surface. Although people happily apply it to all kinds of surfaces that are not like that. But in some sense, to apply the ray model, you really need not the real distribution of normals of your very small scale surface, but you need to kind of average down to some scale around the size of the wavelength. So this is a long way of saying, I guess, that for the ray model, it applies directly to surfaces where the hills and valleys are large compared to wavelengths. But it can be fit pretty effectively to lots of surfaces that don't have that property. For the diffraction integrals, you don't really have to have a constraint on the length scales there, except that this assumption that you can use a locally flat sort of a tangent plane approximation to the surface to predict the reflected field. It starts to get very erroneous if you have highly curved surfaces. They don't really reflect. So again, both of them, they are arguably or provably accurate in the case where things are very slowly varying compared to wavelengths, and then they tend to work surprisingly well in cases where they're curvature. Thank you.
Question, in your picture of wave scattering, you've got monochromatic light coming in.
Yes.
So I assume you're going to get back to that.
I won't come too much back to it except to say that when we do the simulations that I will do, they are all based on sifting things out by frequency first, so they're all for monochromatic light, and we repeat them many times across the visible spectrum in order to get the effects of scattering over the work. Cool. Any other questions with this? Okay, so I spend my time thinking about surfaces some of the time, but then there are a lot of things that you want to render in the world, such as I don't know, furry pets, or your friends and family, or your clothing and other textiles, where the things that are there in the scene are not really surfaces; they're more one-dimensional, sort of fiber kind of objects. So if you look at hair, you can find all kinds of fibers that have lots of different shapes and structures, from very curly to very straight. And fundamentally, what you need to render these things is some model for what happens when light interacts with one of these fibers. And typically, you try to avoid thinking about resolving stuff across the width of the fiber, and you think of the fiber as a one-dimensional object. Some of the things that happen here are multiple scattering is really important for light-colored hair that leads to light that travels and spreads out through a mass of hair. And if you sort of think about what's going to happen, what's the simplest prediction you can make, you can think of a fiber as being like a cylinder. It has surface and extrusion, so its surface normals are all perpendicular to a particular direction. And when light comes in from some direction, it will reflect across that normal. And the geometry of the situation means that all of the reflected rays are going to have the same angle to the fiber as the incident ray. And so you get light that comes in from one direction and goes out on a whole cone of directions, where the cone is centered on the fiber direction. So this has been known in graphics for a long time. This is a Kajia K's 1989 teddy bear that was one of the first to use this kind of model. It basically predicts that when you look at a bunch of hair that is kind of combed so that it's mostly parallel, you expect to see highlights that run across the direction of the fibers. And there are some other phenomena that you'll notice if you look at hair fibers. So, of course, this highlight is not, even if the hair was perfectly combed, this highlight is not perfectly sharp. Specular reflection sort of spreads out to some extent due to roughness in the hair. And I'll talk in a minute about an asymmetric structure that tends to lead to a sifting out of light, so you have an uncolored highlight in one place and a secondary colored highlight in another place. Here's another picture where you can see maybe more clearly the white primary highlight and the colored secondary highlight. So the models that are used for rendering hair and fur and other fibers, usually when people are rendering textile fibers, they just use the hair models because they're already implemented and they sort of apply. They're all based on ray optics, and kind of have a similar flavor to the microfacet model. The idea being that you want to look at a small piece of your object, assume that it has sort of some random variation, and you're going to average over the random variation. So the way this plays out for fibers is you assume that you have a pigmented dielectric cylinder, essentially, So for a hair, that means you're assuming the interior is all homogeneous and uniform, and it has some absorption. And then on the surface, you have some structure that you think of as kind of random, and you basically think of it as it presents a randomly varying normal to the light that arrives. The interesting thing about hair fibers is that because they grow with this cuticle that lays on scales as the fiber grows, this normal distribution is kind of asymmetric, but the most likely normal is shifted toward one side, and that leads to some of the appearance effects. So again, because we're trying to replace this rather than build on it, I will not show the details. But the piece of structure that's important for the work that's coming is about sort of how these models get built at the large scale mathematically. And the way that they're put together is there are some arguments that are made by drawing the slice in this kind of longitudinal plane, where the basic phenomenon is light will come in from some direction and it will reflect at an angle that goes into that specular cone. It might also transmit and reflect internally, or it might transmit and go out the other side. And so you can model the light as having several components depending on what sequence of reflections and transmissions happen. And then if you have a surface that presents a most likely normal that is sort of not perpendicular to the axis of this fiber, then an interesting thing happens, which is that these different reflection components now come out at different angles. So this guy reflected on the top surface, and this one reflected at the back, ended up with different angles coming out. And this is what is responsible for that multiple highlight effect, where you have one highlight from the surface and then the one that is colored because it went through the interior. So these effects of surface roughness in this longitudinal direction basically serve to take that ideal specular cone and just blur it out and possibly shift it to one side or another. I'm going to use the nomenclature of RTT and TRT to talk about these components because that's just labeling them by the sequence of reflection and transmission events that happen. So then if you slice it the other way, you can ask, what picture do you see if you think of the cross-section of the fibers and the fibers going this way, and we send in a bunch of parallel rays from the left there. And these rays will hit the cylinder at different angles, and they'll take different paths refracting through this, in this case, circular cross-section. And a kind of neat thing is this turns out to be the same picture that you use to make simple arguments about the paths of rays in a spherical water droplet in the atmosphere. So a classical argument from Descartes here is that if you solve for the one place where a whole bunch of rays that come in, a whole interval of rays will all go in the same direction, so the derivative of the outgoing angle with respect to the incoming height is 0, that this will tell you where there is a strong reflection that will give rise to the rainbow in the atmosphere. In the rainbow, of course, it's famously colored, and you worry about the change in refractive index with wavelength, but that's not something we're going to worry about for hairs. So it's not that we see rainbows because of this, but that it's this function, it's the same geometry. So this kind of argument saying that we want to know what's the derivative of the outgoing angle with respect to the incoming height away from the axis lets you build models for the distribution of light azimuthally around the fiber. So fibers are rarely circular. In fact, I think in all the hair fibers we've measured, we've never found one that was closer than like 0.9 to 1 to circular. And the acircularity has a big effect on this distribution. And so you can't really get that far making good pictures with the circular model. So most models, or at least the more recent ones, worry about the elliptical cross-section. And then you have a scattering distribution that depends on the orientation of this fiber as well as on the directions.
Do those axes rotate as you go down the fiber typically?
This is a really interesting question. There are some measurements we've been doing actually within the last couple of months that are that have seen this happening, like a sort of steady progression of orientation. Although one of the problems is that like hair is very floppy, and it's hard to say, is its natural state have that rotation in, or did I just accidentally apply the tiniest little amount of torque to it to put it into a twisted state? The conventional wisdom is that these, and I think it's a reasonable assumption, is that at least if things are substantially eccentric, that these axes will probably align with the curvature of the curve of the hair, just because it's has a lower bending stiffness along the short axis. But one of the things that we're trying to find with some of these measurements is just to understand better what really does happen with curly hair when it's very complicated. Okay, so if I zoom out from the fiber model and just look at sort of what does its structure look like as an equation, we end up with something that looks kind of like this. So I'll call this an ESDF, so just like a bidirectional reflectance distribution function, except because it scatters in all directions, I'll say scattering instead of reflectance. Maybe I should say scatterance, but that's kind of a weird word. So this is also a function of incoming and outgoing direction, and it tends to be in the form of a sum of terms, so a different term to represent each of those different modes of reflection and transmission. And then each of the terms is usually modeled as a product of something that's a function of theta and something that's a function of phi. So something that's a function of theta is kind of accounting for how surface roughness causes the specular cone to broaden and become blurred. The thing that's a function of phi is taking care of the effects of different paths going through. I don't know, I always find this picture hard to interpret, but it does show what we mean by the phi angles are as easily around the fiber, and the theta angles are measuring inclination to the moon. So just to show a couple of pictures of what some of the effects are here. Here's a simple rendering of hair where the only thing that's changing is the eccentricity of the cross-section, so going from circular to mildly elliptical to strongly elliptical. My point with this rendering is just that it has a really big effect on how much light goes in a particular direction in a particular configuration. You could conclude from this picture that it gets way brighter when it's elliptical, and that's not quite what happens. It does get much brighter in certain directions. So this kind of model has been used in the film industry quite a lot. Here are some figures from papers that Disney is nice about writing papers about their models so that we know what they're actually doing instead of just having to guess that they must be doing something related to what we do in research. Okay. So one last thing I want to introduce is just the idea that these models are all wrong in a certain way. I guess the talk is about why they're wrong in various ways. But one way that they're wrong is with this assumption that the only thing that matters is to completely average over the random distribution of structures that might occur. So classical models really have always averaged over this. This is a really reasonable thing to do if you're in the lab and you're trying to measure like a big patch of surface and match it to a VRDF model. But if you're trying to make a rendering of an iPhone or something, like a product rendering or other kinds of things where you're going to look at it up close, this stationary assumption is really not such a great one. And really what you need is a VRDF that's just averaged over a pixel-sized area of surface. And even though surface roughness details are smaller than pixels, they're not enough smaller that they completely average out. So here's a little illustration to illustrate this. So here I have a rendering of a flat surface that just has a little height field applied to it. So like some random noise. And this random height variation causes little reflections of the light source to occur. And if I were to render this at 100 pixels across, you would just see a nice smooth average thing. But I want it at the scale where I'm rendering it, I can see that noise. And so if I look at one little section here, here is at about the right scale, the grayscale height field that describes the geometry of the surface that was rendered there. And if I look at the image that I would get if I rendered it at that scale. Here, I'm looking at like a very shiny surface where I have lots of little reflections of the light. Yeah, the point here is just that if these are the pixels, you know, it's true that each of them is averaging over several reflections, but there's nowhere near large enough areas that you could just replace this completely by the mean and get the right looking picture. Here's a practical illustration of just sort of commonly occurring textured plastic exhibiting this kind of literary behavior. If you have Apple computing equipment, that's also a great place to find this kind of phenomenon because they have surface roughness that is in the right range to make this very obvious. So the same kind of thing is true of hair, that one of the things that has been frustrating me for the last few years about trying to get renderings of hair, this is a photo of hair, but getting renderings of hair to look right, is that it's very hard to get the irregularities that show up along the fibers to look right. And I think, again, this is, you can think of this in kind of the same, through the same lens, that we're just averaging over too much, or averaging completely over the distribution when actually there's a lot of random variation left in the scale that we're interested in. Sorry, enlargement here. So here's an illustration for hair that you would initially say is not colored at all, so black hair. And if you look really closely to this, I don't know how easy it is to see on the projector. Here's another example of some different black hair. But you start to see some color in the noise here. So, you know, standing back from across the park, you would just see a smooth reflective highlight from this person. Standing at a normal distance, you can see a lot of texture, and looking close, you can really see some noise in that texture. And once you start realizing that the noise is there, you start to realize that that's going to be an important part of getting an image to really look right. So some questions that are left open by all these models are, there are some models for inhomogeneous scattering from surfaces to get the noise right across the surface, but no one has done this for fibers, and how can we do this? The fiber models are all based on ray tracing, but fibers are, you know, the widths are measured in microns. This seems like a really dangerous activity to trace rays through it and hope that this is going to be completely accurate. So far, or before us, no one had really worried about this. And then the other question is, what are we missing? I guess I'm skipping part of the background, but some of these inhomogeneous models are based on that diffraction type reflection that I described earlier. And you can ask, what are you losing by going to this very simplified diffraction approximation? You know, can you make a reference solution that shows you what the real answer is? So this led us into a project, really, funded by an NSF project that was interested in building sort of accurate solvers for reflection from certain kinds of structures. Partly to see if we could use them for rendering, but partly to see if just like, can we find out what the real answer is that we're trying to approximate with all these other methods, so that we could do a better job of optimizing things that might be fast enough to render. So I could not have done this at all without a whole team of people who are all now more expert at this than I am. So these two PhD students, Blair Yu, who is a current PhD student, and Ben Xia, who is recently graduated and is postdoc at EPFL. And then highly expert collaborators that tell us how to do things. So David, you guys all know, Eric Michelson at Michigan is someone who's done a lot of work on electromagnetic calculations for radio and radar. You just change the length scale and it's kind of the same problem. And then Bruce Walter in PCG is someone who is a real expert on all these different surface reflection models. Okay, so I want to talk about two projects here that are both trying to kind of do accurate wave reflection calculations, one for fibers and one for surfaces. And I'll start with the fiber one because it was the one we did first. So I'm summarizing this as wave scattering for fibers in 2.5 dimensions. So this is a project that Andy did with Bruce and Eric and David and I. the goal of this project really was to start to answer the question, like, what are the differences between the predictions of the ray model and the wave model when you talk about reflection from fibers that are graphics relevant? So I would say fibers that are on the scale of textile fibers, which are maybe 10 to 20 microns in diameter, up through hair fibers that are maybe 70 to 100 some microns in diameter. And what the requirement for this is some kind of full wave simulation, something that can really not leave out any of the effects of that are predicted by Maxwell's equations, but somehow is tractable. And this tractable part is a challenge with these simulations. And the key simplification that we picked here that made this work is to say we're only going to look at fibers that have translational symmetry. So they're extrusions, that everything is constant along the axis of the fiber. And the reason this is super important here is that it changes the PDE that needs solving, which I'll talk about in a minute, but it changes it from something that's defined in 3D space to something that you can actually solve in a 2D projection of that space because you know exactly what happens along the axial dimension. It turns out that there's an analytic solution that's available for the circular case, which was very handy for testing things, but not so handy for hair fibers because they're not really circular. And then we developed a numerical method that works for arbitrary cross-sections, such as optical. And then the question of what you actually do with this in order to make a picture, because it only is handling part of the problem, like it only does perfectly smooth fibers. So what we did is to replace that azimuthal factor in a conventional hair model. So keep the factor that talks about how does light spread away from the specular cone, and replace the factor that talks about how light is spread along the cone or around the fiber. So it's only half the story, but at least half is better than not any. And this longitudinal factor, I think you could argue the models that people use there are hardly even really ray optics models. They're just like empirical blurring rules for spreading out the light off of that. So the goal then is to make a simulation for the scattering of a wave by a fiber that has an arbitrary cross-section. And so I want to say a little bit about kind of the how you set up a scattering problem like this, and then how we set it up and solved it. So in the ray optics world, you tend to think of scattering in terms of I had a bunch of rays and they encountered some geometry and they scattered. In the wave way of thinking about things, you think of starting with some incident fields that in the absence of an object, you know exactly what they would do in your domain. And then you put an object there and you ask what changes about the wave field that is now supported in that domain by this object. So the thing that you actually want to predict, or the thing that you might ask is like, what are the fields that you end up seeing in space? And these are called total fields. The reason for the word total is because we're making a sum of something in a minute. So a couple of different approaches that are widely used for this are FDTE, the finite difference time domain method, which looks at the problem and observes that you can make a really nice finite difference discretization of it. It's a great algorithm, but it really needs to be applied at smaller scales than the ones that we're interested in, where the domain is not so many wavelengths across, because the problem scales really badly because in the 3D domain you have x by y by z size. You're going to need 8 to 10 samples per wavelength across the whole domain, and then you have to do enough iterations to get the waves to propagate across the whole domain. So you have just an awful lot of factors of the length scale in there, and it doesn't scale to the sizes. The one that we'll actually use is the boundary element method, which is based on the frequency domain formulation. So assuming a monochromatic incident field or monochromatic everything field, and works by transforming on paper the problem into an integral equation on the boundary and then discretizing and solving that. So let me dive into this a little bit. Going through all the details can be complicated, so I'm going to try to take a slice through not too many of the details. But so the problem that we want to solve now, it can be stated as I have space. It has some electric and magnetic fields in it. So E and H are vector fields in the space. So far, it doesn't matter whether we're in 2 or 3 dimensions right And the space is not homogeneous. It has one region that is one material and one region that's another material. So like for a fiber, this will be a dielectric material that is the stuff the fiber is made out of, and this will be air or vacuum or something like that. And the rule of the game is that these fields have to satisfy Maxwell's equations all the time. The equations I've written here are a form of these equations that apply to these time harmonic fields. So E and H here are complex value vector fields that encode both the amplitude and the phase of these fields, but the fields are all assumed to be oscillating at a fixed frequency everywhere all the time. So these are related to one another by these equations. So you'll notice that these equations have mu and epsilon in them. Mu and epsilon are material parameters that are different between the two regions. So the equation that holds in here and the equation that holds out here are slightly different. And we can expect to see a discontinuity across the surface. So that discontinuity across the surface is governed by some boundary equations that insist that the tangential components of these fields are continuous across that interface. So here, E1 and E2 are like the limiting values of the fields as you approach from the two sides. So the question is, how do I actually solve a problem like this? The idea of the boundary element method is to recognize, or again, the idea of the boundary integral formulation of the problem is to recognize that the fields that you find in the space outside and inside your object are not just lineal functions, they are a very special class of functions. And this principle known as the surface equivalence principle, which is something that's a particular instance of something that shows up in a lot of domains, but says that if under the right assumption, so in this is homogeneous space and there are no sources in it, I can parameterize the fields that are allowed to be outside the object with just a source that is on the boundary of the object, and that essentially propagates out and defines the entire field. And likewise, if I put a source on the surface, I can also, using different material properties, I can define what happens in the inside. And so this is kind of cool from a computational standpoint, because you could say that I took an unknown that used to be a vector field over 3D space, or really a pair of vector fields, and I made it into a vector field that is just a source on a surface, so it's one dimension lower. And every field that's a valid solution out here can be generated by one of these two-dimensional fields on the surface. So the two-dimensional fields are going to wind up being currents, so magnetic and electric currents. They are fictitious. There are no currents really there, which is good if they're going to be magnetic currents. And these currents are the unknowns in the problem, and the currents define the fields in those two regions. For the standpoint of kind of understanding the formulation, the only thing we need to say is that there's a linear relationship between the currents on the surface and the fields anywhere in space. And there are some integrals that we can write down that will let you, if I want to know what is our electric and magnetic fields here, maybe you can integrate something over that source and get the answer. So there's one of these for the exterior that gives you the scattered fields in the exterior, and one of these for the interior.
We're doing this for like each pair, or is this for bunches of pairs?
So this is for one hair.
This is for one pair.
Yes.
Okay. And then, like, how do you do it for like 1,000 million pairs?
I'll come back to that.
Okay. Thank you.
I'm just realizing one thing that I didn't say is that the field out here is expressed as a sum of whatever the incident field was that I put there in the first place, and another field that is the scattered field, which is the one that's generated by these currents. If I take my problem now, I have these two current distributions of the inside and outside, or inside and outside of the boundary. One that's on the boundary that is defining what's happening outside, and one that's defining what's happening inside. I can use those to compute the fields at the boundary. So the fields at the boundary are influenced by the sources everywhere. And then I can apply the boundary condition that says what happens, what has to be the relationship between the fields on the two sides. And by doing that, I can get an integral equation that is defined on the boundary that has as its solution the currents that are going to be the sources in the fields. So the boundary element method is then to take that equation, the integral equation on the boundary, discretize it using finite elements, and lo and behold, you get something that you can solve a linear system where the unknowns in the system are the currents on the surface. They're the coefficients for a bunch of basis functions for the currents on the surface. The right-hand side is related to the incident fields, and the matrix is something where the entries tell me how much does a current here influence the field somewhere else. And this whole thing says that the fields generated by the currents satisfy the boundary condition, and you end up with something that you can solve. So in the next project, I'll come back a little bit more to the computational methods for this. But once you know those currents, then you can use those source field relations, the integrals that let you compute the fields anywhere you want from the currents on the surface. And you can use those far away from the surface to get scattering intensity in different directions. You only care about the source field relation for the outside. You can compute what's happening inside if you want, but you don't need to for the far field. So we do this in a 2D projection. And I'll say that this 2D projection is something that still can handle, if this is my fiber, it still can handle light that's arriving from any direction you like. It's just that because of the translational symmetry of the fiber, it will always reflect everything exactly into a cone. And so in some sense, the whole problem stays in 2 dimensions. So here are some illustrations of simulations for a range of different incident fields for a particular simple geometry. So here I have a circle that's the geometry. It has a dielectric inside that is about typical of hair. And you can see that the total fields I get out of the simulation show both some kind of ray-like behaviors, like I can recognize the path that refracts through the inside here, but also some very wave-like behaviors. There are diffraction patterns. There's light going in directions that it would not be going under the ray model. So coming to your question, how do I make pictures with all of this? There's not just one fiber. So the idea is to assume that all of my fibers have the same cross-section, or they have some small number of cross-sections, so that I can make a model for a particular cross-section and then use that to render a bunch of hair. So the idea is to do a bunch of simulations using incident fields that come from a bunch of directions. I have to sample both this is the hair, both the azimuthal direction and the longitudinal direction. So each of those simulations produces a scattered field. And the scattered field tells me, when the light comes from here, how is it spread around the reflection cone. So I end up with a 3-dimensional table, which is doable. It's not too terrible. And then I can store that table, and then during rendering, when somebody asks me, okay, this fiber is lit from this direction, and I'm viewing it from that direction, what's my reflection factor? I use the table for the azimuthal component, and this is the thing that is a function of the azimuthal angles, and I fall back on previous work for the component that's a function of the longitudinal angle, the thing that tells me how much does light spread across the cone. And that gives me a way to make pictures. First, I'll just make pictures of that table, slices of that table. So these are potentially a little bit difficult to interpret right away pictures, but they're slices of the table where the 2 axes are the 2 azimuthal angles. So one vertical row here is all of the configurations with light coming from one direction. One horizontal row is all of the configurations that are going to a particular direction. And I guess maybe the thing in the interest of time to observe here is that here are simulations using conventional ray models, and here are the outputs of the wave model. And there are a few things that are different here. This bright line here is the forward direction, and it seems like there's a lot more light concentrated in the forward direction in all of these examples. And then when things get very small, so this is like a 1.6 micron ellipse, I start to see a lot of color effects, which is maybe not surprising when things are that small. The wavelengths across the visible range are changing a lot relative to the size of the object. So if I use this in a renderer, I basically take a renderer that supports hair, and I drop in this model as a replacement for the hair model. And one thing that you can find is that if you render very thin fibers, so spider silk is an example of a very thin fiber, that you get strong iridescent color that depends on the angle and can be predicted by this model. This is kind of a qualitative match to a particular photo. We don't know anything about the exact conditions of this spider web, but it illustrates that you can get a similar visual effect, where if you just use the ray model, you end up with something that looks quite different. So the other thing that's important, pardon me, is that forward scattering, which turns out to be a component that is due to diffraction by the overall cylinder. And this is something that was a surprise because most people, including us who've been measuring fibers for graphics, have been using setups that can't actually get that close to the forward direction, so we didn't really know what was going on there. And it turns out that this model predicts a lot more light going in the forward direction than the ray model, because the ray model assumes that light misses the fiber, where in fact the fiber affects the wave over a region of space that is larger than just the geometric extent. So that's essentially how it's able to scatter more light forward. So in backlit configurations, things look a lot brighter, like here. And then if you look at a big massive fur, like this critter here, if we render this with a ray versus wave model, you can see a difference that I would summarize as the direct reflections are pretty similar. They're sort of coming back toward the viewer in a place where the two models agree fairly well. But the bulk distribution of light in the medium is quite different because this forward scattering leads to light diffusing in a very different way. So to summarize this here, this is the first fiber model in graphics that was based on wave scattering. The question that we started out with was, what is going to be different about the predictions in this model? We were hoping the answer wouldn't be nothing at all. In fact, it did find a couple of things, one unsurprising and one, well, at the time surprising, and maybe in retrospect less surprising. So the unsurprising one to me is that when you make fibers very thin, they get iridescent because the scattering depends a lot on wavelength at that scale. But the other thing that's really important here, and which is now starting to make its way out into models people are using in practice, is that there's this strong forward scattering lobe that was missing from the previous models that is due to diffraction around the fibers. So things that are left out are, we have no way of modeling irregularities along the fibers. We had to assume everything was perfect extrusion. And that means that we still don't know, at this point, we don't know the implications of wave optics for the effects of roughness and sort of asymmetric cuticle structure. We have a little bit more to say about this, but that's the project that's going to fall off. Okay, so I wanted to show you another project, a more recent one. This is work that's currently in submission. And I'll have to construct a little bit quicker slice through it than I had initially planned. So the goal of this is Blair's work, working with Mandy and a bunch of the rest of us. The goal of this work was to do something similar to this fiber model, but to do it for rough surfaces. So there are a lot of models out there, as I said, for scattering from rough surfaces, and many of them can give you an answer for light scattering from a small area. But if your areas are as small as pixels in a high resolution image, you might wonder, how much are you losing by using ray optics And if your surfaces have a lot of complicated structure, you could ask how much are you losing by consuming simple diffraction models. And so our goal is to be able to compute high-quality solutions. The key simplification here is to use height field surfaces. So the surface is assumed to be a height field, the slopes are limited, so that we're going to be able to just sample it on a regular grid and have height be the only geometric variable. And it turns out the regular grid structure actually simplifies a bunch of things in the implementation. And so that is part of what makes it possible for us to scale this up to pretty large cases. So the computational approach is to apply the boundary element method again, except this time it's on a surface rather than a closed contour. And one of the things that makes it work is a scheme for accelerating the matrix multiplies that are part of the solve. So here's a picture of the setup, the boundary element setup here. It's very much the same. There are fields out here that include incident and scattered fields and fields in the interior, and they're parameterized by some currents on the surface. One thing that's different is that the surface is open on the edges. So here we have to end the domain somewhere, and we do that by just arranging the simulations to make sure that things have died down to small values by the time we cut the domain. So let me just give you a quick sketch of how the clever part of this works. So in order to do this, I'm going to have to open up the box just a little bit more. So this is the AX equals B that we need to solve for the boundary element method. So I have an unknown vector, which is coefficients for surface currents. I have a known vector, which is coefficients describing the incident field of the surface. And then I have a matrix that tells me how these currents influence the boundary conditions. So that matrix, if you fiddle with things a little bit, can be made into a symmetric matrix. So it's a symmetric matrix with complex value entries. We adopted INRES as the solver for this. So this is an iterative matrix solver, meaning that it's going to do a computation where the bottleneck is going to be taking sort of trial values of this vector and multiplying them by that matrix. And that's the thing that is going to take up all the time. So that's the thing I need to think about doing efficiently. I'm going to skip that quadrant and go straight to this one. So the idea here is that I have the entries in this matrix are basically talking about interactions by radiation between two different basis functions on the surface. So this basis function is radiating some field, and this basis function is receiving it. The acceleration approach is based on taking advantage of the fact that this radiation, sort of the Green's function that describes the transport between these two things, is shift invariant. And because if you see a shift invariant function, you think there's got to be a convolution somewhere, but the convolution isn't in the domain on the surface because that surface is conforming to the surface, and that grid is conforming to the surface. So the idea here is essentially to take what's going on the surface, resample it onto a three-dimensional grid, do the shift invariant part with the convolution on that grid, and then resample it back onto the surface. And so this boils down to a kernel for matrix multiplication that has a sparse matrix multiply that is taking all of the coefficients for my basis functions and turning them into a set of sources on a grid. A convolution that is sort of transporting waves through the grid, and another sparse multiplication that's mapping back down to the surface. And so this is the core of high performance implementation for this thing on GPUs. There's another sparse matrix here that I'll ignore for the moment. So this means that the main solver iteration here is doing a bunch of matrix multiplies with this matrix Z. And so if I can get these sparse matrices written down somewhere and get the function that I'm convolving with written down somewhere, then I can do these using fast Fourier transforms and sparse multiplies. And that's what we do. So the design of the whole system is based on making sure that I can take x, which is a fairly small vector, transmitted to the GPU, keep all of these matrices on the GPU where I can do the operations and then get the small matrix y back. So Blair has made a really nice implementation of this, which for the big problems that we do is running on 4 big GPUs, where she has sort of partitioned all of the pieces of data so they completely fill the memory of all of the GPUs we've got. And then we can do some domains that are pretty big for us. So I'm going to skip to one example here because it's the most interesting one, I think. So this is a case where you really need the full solution in order to get a good answer. So looking at the left here, I have a height field surface here that basically looks like I took a cube and I stamped the corner of the cube into a surface a bunch of times and made these little quarter cube shaped indentations, which are inclined to reflect, at least from a ray perspective, reflect 3 times and go back toward the source. We tried a bunch of different models that are based on diffraction theories of various levels of accuracy, and not surprisingly, none of them can give you a reflection pattern that looks anything like the one that you get from the full solution, because you have to be able to solve for this influence between different parts of the surface in order to get the full answer. So what we have here are circles that are showing how much light goes to each direction in the hemisphere, and circled over here with dots that are showing where the light is coming from. So here with the light coming from straight overhead, a bunch of light goes straight back in a few other places. And with the light coming from above, a bunch of the light goes back to the above direction. Here's another example where the things that are missed are mostly interference effects that are really between different multiple reflection paths in an array of little spherical pits. This one is actually motivated by a surface that somebody we're talking to wants to actually make. Okay, so to summarize this, this is a project about computing reference solutions for scattering from small areas of surface. So it's basically as if I shine the laser on my surface and I measure the light that was reflected. If you're interested in making models for that phenomenon and you want to study how accurate they are, this is a really nice tool to have in your toolbox. At this time, it is not directly a model for rendering anything, because it's just too darn slow. So we can't even really afford to tabulate a whole BRDF with this because it's so many direction pairs to do, and it takes several hours per simulation. So the applications of this are for developing new models and potentially for designing structured surfaces to have particular reflection techniques. So I will, as I had kind of predicted, have to skip the last project. And I will leave it there. So I continue to be interested in this general area of trying to explore what the wave model predicts for situations where we have always used simpler models. I have to say that I was worried going into this project that we would find that the answer all the time is the models you're already using are just fine, stop doing expensive computations. And it's been interesting that sometimes is the answer, and it's sometimes not been the answer. So this is just a teaser from the project that I skipped that is showing how we can now make a simulation of reflection from fibers that actually gives you some of that spatially varying color noise and this is from an approximated model of 3D scattering from rough fibers. So acknowledging co-authors, people whose work I showed here, and people who funded it.
So we're right around time, but maybe a question or 2 questions. John?
I've been interested in singularity theory through my career, and you have caustics in the ray fields that come from medicine, and there are modifications of that have been developed for looking at the effect of having finite wavelengths. Have you tried to use caustics and singularities in the fields at all, in the calculations that you're doing?
So, I guess it depends on what you mean by use, but we've certainly observed that there are caustics and singularities in the predictions of the rate.
Well, so by use, I mean that you try to locate them.
Right, right. So,
And then
yeah,
build approximations based upon
right.
that.
So for the ray-based fiber reflection models, this is something that we have done and people have typically done, or I guess we initiated and people have typically followed, is so when you have these fibers, they produce strong glints in particular directions, and these are basically at the singularities of the folds in the mapping from incoming position to outgoing direction. And finding those is how you can locate those glints. And so a simple model for the bright glints in the azimuthal distribution is essentially to just locate that singularity, use sort of a second order, use the second derivative to estimate how much energy is piling up there, and then like put a blob with that much energy at that point in the distribution. And this is something that has worked pretty well for making, for placing the glints that result from circular or elliptical fibers into the right places in the distribution. I guess the history of that is I was excited about this and thought this was pretty cool, and some of the initial models that we made used this. There are some other things that are kind of all handled in one big piece by sort of just putting a blurring kernel over the whole thing and doing a little bit more numerical calculation. So a lot of the later models are basically based on a quadrature that just runs over that and doesn't try to locate the singularity, which I think is kind of too bad. But,
Yeah, so with the rough surface.
right, there are singularities all over the place.
Right.
Yeah. Yeah. We have not tried to locate those, and indeed, the inability to do that has led us to smooth the problem a little bit in the ray-based models we've done for that part of the problem, where we essentially, either you could say we assume that the light source always has a certain extent, or you could say we assume that the surface has a little bit of roughness to it, but so that you can compute all these patterns without having to worry about stepping over the singularities. But I think it would be really interesting to think about, because you could associate them with curves on the surface that are the reflection points that produce them. One of the problems, I guess, is that switching to the wave model essentially tells you that, like, okay, these singularities are important, but they don't really produce the kind of sharp folds that are predicted there. Although there may be some way to still use them as the seed for an approximation, but I have no problem with.
So, given
That was a
timing-
long answer
yeah.
for the one question.
Given timing and the fact that I know that Steve and I have someplace to be in 8 minutes as well, maybe let's thank Steve again.